Hi guys, what's up? Welcome back to Chem 1 BSI. My name is Roane. Today we're going to be going over some spontaneity, entropy, that sort of stuff. This is going to be a relatively short lecture, and it's just going to be some kind of basic ground rules for this sort of stuff. So when we talk about entropy, the first thing I want to talk about is spontaneity. So a lot of you guys probably know this, but spontaneous reactions and non-spontaneous reactions. But spontaneous reaction is a reaction that can happen on its own without any sort of intervention, so without any addition of energy, addition of anything. Spontaneous reactions can just happen on their own. Non-spontaneous reactions are the exact opposite. So you put two things together, they won't do anything unless you add a certain amount of energy or another chemical, something like that. But those kind of reactions, they will release or gain, they will have some sort of energy transfer. Okay, that happens in all sort of chemical reactions. There's going to be some sort of energy transfer. Some of the energy that is transferred cannot be directly used to do work. So you get energy, but you can't really use that energy. That happens in some of these chemical reactions. Or you lose energy, that energy can't be used to do work. Okay, that amount of energy is called entropy. Okay, so entropy is the amount of energy you have that is unable to do work. And another way you'll hear entropy is a measure of randomness or chaos, and it can sound kind of contradictory to have a measurement of randomness. But this is just kind of like it's kind of like a chemistry measure. It might not be 100% true, but it's just our way of measuring this sort of stuff. Okay. Another small part of entropy is microstates. So microstates are different ways we can arrange energy of a system. So if we look at this little column here, we can see we have two containers and we have some particles in the middle. The particles here will be energy, okay? And we can hold or distribute these particles of energy in multiple different ways, okay? So we can have all of the particles on the left side, that's one microstate. We can have 3 particles on the left and 1 particle on the right, but we can organize those in different ways. So we can have blue by itself, yellow by itself, red by itself, and purple by itself. Okay, those are all different microstates. Okay, we can have 2 particles on each side, but again, each different combination of particles is its own microstate. We can have 1 particle on the left, so on and so forth, until we get all particles on the right. Okay, each of these different combinations is its own microstate. Okay, so in this example, we have 16 microstates. Okay, however, the more microstates any sort of system has, the more microstates you have, the more entropy you have. Okay, so the more microstates, the more entropy. If I had another system here that had 9 microstates, this one would obviously have more entropy. Okay, so that's how you can relate entropy to microstates. The last slide is just about how entropy relates to other certain chemical properties. So the main chemical property that entropy can relate to is the state of matter your substance is in. So a gaseous compound is going to have the highest entropy and solids will have the lowest. So if I was going to compare all the states of water, so if I had water vapor, water, and ice, okay, entropy is going to decrease as you go from gases to solids. So as I'm freezing my substance as I'm condensing my gas into a liquid, as I'm freezing my liquid into a solid, I'm going to be losing entropy. My entropy is going to be lowering, and when I melt my ice into a liquid, when I boil my liquid into a gas, that's going to increase my entropy. Okay, and the last thing is entropy can also relate to molar mass. So the higher the molar mass a substance has, the higher the entropy, right? So if I have a bunch of different substances that all have different molar masses, okay, I can relate entropy to those, and I can say how entropy changes throughout those given molecules based on the molar masses. The ones with the higher molar masses are going to be higher in entropy, and the ones with lower molar masses are going to be lower in entropy. However, just for the sake, I want you guys to make sure that you know that the states of matter are more important when it comes to entropy than molar mass. So if I have some sort of gas here, right, and this has a molar mass of 14 grams per mole, and then I have a liquid, and this has a molar mass of let's say like 30 grams per mole. Okay, so like these two things kind of contradict the 2 points up here, right? So this says that gases have a higher entropy, and then the bottom point says that higher molar mass would have a higher entropy, and here we have a gas with lower molar mass. Okay, but gas, the state of matter, will always be the more important one. Okay, so this, because this is a gas, we know that this is going to be higher, so the entropy is going to decrease when you go from gas to liquid. Okay, I hope that helped you guys. Feel free to stop by our office hours or do our supplemental worksheet with the subject. Feel free to drop by if you have any questions regarding entropy, spontaneity, any of that sort of stuff. All that sort of stuff can be found in the description. But yeah, I hope that helped, and I hope to see you guys next week.